questions. Okay, you have an opportunity to ask questions. Someone wanted to join. Okay, all right. So now, so your surface, you decompose it into three surfaces: S1, S2. But you know that S1 and S2 are just the same surfaces. So I'm just going to call it S. Now, with a dot product, if I give you, it's from the definition of a dot product. Actually, a dot product is defined to be E dot ds1 is defined to be E, which is the magnitude of the vector. The vector and the magnitude, they are very different things, guys. ds1 and ds1 as a vector is a very different thing. Then cos of the angle between them. Okay, so let's call that angle between them alpha. Now, if E is in the z direction and S1 is also up, this is how we show the same, meaning they have got the same direction, meaning the angle between them is 0. So what is cos of 0 is going to give us 1. So here the answer is just going to be E ds, because we know that the angle between them is 0 and cos 0 is 1. This is why we just check if they are collinear or in the same direction, if they are parallel, collinear, whatever that you want to see. So whenever you're decomposing this integral, it's the formula for flux is we say the integral la formule intégrale d'un flux électrostatique est égal à it's E dot ds as a vector. Then you decompose this into 2 according to the surface. So here it's a cylinder. E dot ds1 plus E dot ds2 plus double integral of E dot ds3, where this is our surface cylinder which cut through the plan infinite. So this is a section. This is a section that was enclosed of the charges. Then of course this is the same surface as this. So now here the dot product here, but you multiply these two as magnitudes. Why you could have, if you want to represent these two vectors as magnitude, you just get the magnitude part, which is just E. So here you're going to have the integral of E, then you multiply with the ds1. Oh, but before you do the multiplication, you have to check whoosh, are they in the same direction? Is E and ds1 in the same direction? We said that, what did we say about E? This is how we present, by convention, this is how we present the surfaces, which are the direction of the surfaces. So we said E has one variable and it's in the z direction, right? Use it. Okay, so E is either up or down. So the question is E and ds1 the same direction? The answer is yes. So if yes, multiply them and forget, with the dot product you forget about the vectors. If you see a difference between this step and this step, I no longer have the vectors. You do the same with the second part. Is E and ds2 in the same direction? Okay, is E and ds2 the same direction? Yes, they're in the same direction. E is in the z direction. So here we're going to have the integral of E ds2. You can now multiply their magnitudes. Now, the interesting thing is, upper is E and ds2 in the same direction. By convention, the direction of this surface is in this direction, but E is in only this direction. This is also the importance of knowing the direction of E. Okay. So we say for you to be a good mathematician or engineer, you have to be lazy. What I mean by being lazy is, if you are, that is, you can't manage to, what I mean by being lazy is not like you're not studying or shanshan. No. What I mean by being lazy is, if you want to be a good engineer or mathematician, you have to be lazy. What I mean is, if you are lazy enough, basta kupela equation you start looking for, I would say, lazy ways of solving it or ways to solve it. For example, the show electrostatic will have 3 components and 3 variables. So instead of you one method solve manually, you start solving it manually, you find that, oh, okay, the other components are 0, what. You look at the intelligent ways in which you can cut off some variables. You can, that's what you mean by being lazy. If you are lazy enough, it will make you become more innovative, if we can say that. So this is what your fellow scientists discovered methods and gave them to you. Okay. The funny thing is, they have, they thought for you, they show you how to do it, but you're still not understanding. Imagine if they were to tell you to think about it. Because these things that we solve, they are the things that they were thought by someone from nowhere. Iwe bakutontonganisha bakupera n'okupera, but still more now comic. Just know that your friend started from zero to think about these ways of solving. Now they think for you, they even give you how to do it, but you're still finding problems. This world is not fair. So now, yeah, now with these components, and then with an integral, guys, we say if there's a constant inside an integral, you take it out. So how do you know this is a constant? This is a constant par rapport à cette surface. Why? Because on this surface, z is constant. Z is 0. Z, whenever you're moving on this surface, and E is only Z dependent. So on this surface, Z is constant. Okay. So you have we say vous avez le droit de sauter sur l'intégrale. Okay, you have the right to get out of the integral. Then plus E, even here you can get out of the integral ds2. Again I repeat, means however in French, or they'll use it a lot. Or whenever you get out of the whenever you are integrating on this ds1 is a smaller portion of, let's say you have s1, ds1 is like a smaller portion of. So whenever I have the double integral, surface integral actually, or the double integral of the surface, it's just that surface. So E s1 plus E s2. Or however, S1 is equal to S2. So I'm just going to call this S because it's the same. So that is the calculation becomes S plus ES, which is 2ES. So you've seen this giant here has now turned into 2ES. Okay, and this is not a vector. This is a magnitude. There's no arrow on top. You have to know. You just don't have to define what a vector is. You also have to know, identify, and use it. Okay, that's how we use theorem de Gauss. These are the steps that we follow actually. We choose a surface and we call this a surface de Gauss. We choose a surface that will be easier to integrate on. We apply the concept of integration and it will simplify. This is why this is a suitable surface. You learn about Gauss's surface and how to identify a surface. Because of our time, I just give you here, we use a cylinder. And even when you go to your school, you'll be using a cylinder. Don't worry, you won't be using anything else. And next thing now I start develop with you. Now let us also now try to deal with the right hand giant, because from what Gauss said, flux, which is given by the integral form E dot ds, is given by q in over epsilon 0. Always, whenever you have a distribution of charges, boys, whenever you have a distribution of charges here, think of what on a surface. Think of what surface density. So you want to know the amount of charge here. So the amount of charge inside is given by surface density, which is constant. I'm saying it's constant and it's always constant because I'll take it out of the integral. And what is the surface? What is this surface? This surface, you observe, okay, if I call this surface 3, surface 3 is also equal to surface 1. This surface is equal to this. So multiply by the surface, as simple as that. We don't call him surface density for no reason. Okay, so whenever you have Q and you have got a continuous distribution of charges, by continuous distribution of charges, I mean you might have a charged wire, you might have a charged cylinder. As long as they have said this is surface, they are giving you a surface density. Lyonsa pari Q kubikapo expression ya sigma S. So, and that surface will depend on the surface that you have. Here it's sigma S over epsilon 0. This giant, the left-hand side giant, left-hand side was just reduced to 2ES. All this reduced to 2ES. So we can now cancel out S and S. So E is equal to sigma over this is the show electrostatic. Now this is just the magnitude part. Hapo number wasabika direction number. Okay, for it, this to have a direction, we established that it only had one direction. Okay. So that's how you find the show electrostatic using theorem de Gauss as simple and neat as it is. I showed you how to solve this in the video that I recorded. I've also shown you how to do it in this video. Hopefully I'll upload it. Okay, so do you have and look at it. So if you remember, I taught you solid angle, but for now, from my observation, the only thing that you need to see, if you see something like ds, then cos alpha over the whatever is here squared, it can be L squared or R squared. Just know that this is equivalent to elementary solid angle. So this is a method where we use the solid angle to simplify our equations. Once that you have this expression in our equation, so you replace this equation by solid angle for now, since you might have forgotten a solid angle. So whenever I have ds cos alpha over something down squared, this is you replace it by solid angle. Sebo, for example, I'm going to, okay, the other thing again that I'm going to teach you is whenever we have a right angle triangle, something special about the right angle triangle. Whenever you have a right angle triangle, okay, if you use SOHCAHTOA, actually, it's going to give you, should check, I've been teaching my students this. So forget about this kind of thing here, but imagine this is a right angle triangle. Okay, now whenever I have a right angle triangle and then angle maybe alpha, okay, the opposite side will have, let's say this is a vector E. Okay, this is the dE vector, the show electricity. Let's say this is where our charge was Q, and it's giving us this vector dE. Okay, whenever you have, maybe this is a point M, whenever you have a right angle triangle, boys, if you want to know the composition of dE in this direction, here it will just be dE, the magnitude multiplied, the hypotenuse multiplied by sine alpha. The component here will also be the magnitude multiplied by cos alpha. Simple as that. Whenever you have a right angle triangle and you have a vector, these other components, you know what component is this going up? This is the z component, right? So dE will have two components. The z component, what component is this? The y component. Okay, z, d, y. Okay, we have two components. dE can be decomposed into two components. The first component will be dE cos alpha in the y direction plus dE sine alpha in the z direction, as simple as that. So so you get the magnitude of dE. You say dE magnitude, because I'm not talking about direction. You say dE sine alpha, sine for the opposite side. Then the adjacent side it's cos. So then you say dE cos alpha. So if I tell you, okay, decompose dE into two components, and going up, you know that going up is the y direction. This is the for you then that this is the y and the x. If you want, you can take it as, if you're using the 2D, you can say in the y direction, then z direction, or x direction. Or if you're using a 3D, you say this is z and this is y. As simple as that. Is that difficult, boys? Okay. So what you do is so you parameter. So you know that your vector E that will pass through E will come from this to here. This is why your vector, your dE will be dE. Because why am I using dE? Because we have only looked at a smaller portion of the disk. So this is my vector dE. This video will be very important. Okay. Now we know that dE or E, because for you to find the total E, you just integrate. If you, that's what we do with actually that's what we do with a direct method. What we do is we start with a smaller portion, then we just integrate. We apply integral to find the E. This is dE for dq ds. Now for the entire surface, we just integrate. So for dE, you know what? dE or E only has one component. It only has the direction, the z direction, okay? So which means this vector can be decomposed into, so imagine this is a right angle triangle. This is where that idea came from. So this is the right angle triangle, of course. And you should just call this angle alpha. So you know that this dE can be decomposed into two components in it. So the z component and the y component. So what is the decomposition of dE in the z component? So since this is alpha, what is the angle opposite? What's the side opposite? This side. So this side will have dE, the magnitude, then sine alpha. As simple as that. Then the opposite, this adjacent side will have dE cos alpha. As simple as that. So this will be in the z direction, car. Then this will be in the x direction, or I can say ux. Then uz. Unit vector z to show the direction. Okay. So dE en général, peut-être écrit comme, can be written as dE sine alpha in which direction? So you can decompose this in two because we've got an angle alpha and this is a right angle triangle. dE sine alpha, then in the direction of uy, I'm going to take as this as 3D plus dE cos alpha in the direction of what? uz. Oh, from symmetry we've established that the only direction which is valid for E is what? Is z. So the y direction, this component, instead of, because if you solve here, you find that it will even give you 0. So instead of wasting your time because you're too lazy to start doing the manual calculations, you just say from symmetry, we know that our E only has one direction from planes of symmetry. So this component you say is going to be 0. Therefore, from here, from the right angle triangle, decomposing, identifying, saying this is alpha, dE will be what? dE will be equal to dE cos alpha in the z direction, as simple as that. Okay, now here you are not there yet, so now your job is to find dE, which is that's the magnitude. Then also your job is to find or maybe here you just find dE actually. Okay, so now what would be dE? Okay, dE, this is a vector, so dE is the magnitude part, so dE is the show electrostatic. So how do you define a show electrostatic? So let's imagine this distance is r, the distance from this point, let's say pm. Okay, how do you calculate dE? How do you calculate the show electrostatic? I just introduced to you. Okay, so show electrostatic in general is given by the charge. What is the charge here? dq, because we're calculating dE. So it's going to be dq over this constant 4 pi epsilon 0. Then we say pm from the charge to the point m over pm to the power 3. This is always the formula for show electrostatic, will always be the same. The only thing that will be changing is what is the charge? dq. What's the distance called? pm over pm to the power cubed. As simple as this. Oh, this is a continuous surface distribution of charges. So where there's charge G, I remplace by the formula. So now what will be the formula for dq? The formula for dq will be surface density multiplied by the surface where dq is. The surface where dq is, because we're talking about dq, so it will be ds. ds. As simple as that. Step by step, step by step, step by step. This video will be very important. And if it might not be important now, it will be important later in the future. You'll be looking at it when I'm not even there. You'll be listening to my voice. And you'll be seeing it. Fear then should be cash. That's it. So now where there's the Q, put sigma ds. First I'm going to fake it. That's it. I should do it simple. So you put sigma ds over 4 pi epsilon 0. I'm just Whatever I'm doing here is just basic algebra that you know. You shouldn't be confused. PM to the power 3. Okay. Now, you just don't remplace on Disque. You also find PM. Okay. What is PM? Okay. So, here where there's PM, okay, PM is equal to R. I'm just calling it R. Or I can also put the unit vector. I can say the magnitude of PM is R, then the unit vector you are. Okay. So here, what I will do is I will say this is equal to sigma ds over 4 pi epsilon 0. What is PM? PM is equivalent to R, the magnitude of that of PM is R, and the unit vector you are to show the direction because this is a vector over PM. Magnitude of PM is R to the power 3 R3. Okay, so this can simplify to be sigma ds over 4 pi epsilon 0. Okay, so this R and R, 1 R here will cancel, remain with 2. So here we're going to have sigma ds 4 pi, we're going to have ur over r squared. Okay, now the question here in the equation of only establish that it's dE is the magnitude of this.
No, Mr. Chilivia.
Yes.
So in calculation, like, do they give epsilon 0 or?
No, you answer if you observe. Thank you very much for that answer. Your answer is always as a function of epsilon 0. If you've seen for the plan fini our answer, the show electrostatic for our answer was giving us sigma over 2 epsilon 0. Even sigma actually don't give. Epsilon 0 don't give. You leave your answer like this. Actually, here you'll be solving a lot of variables, finding variables. You won't be finding specific answers. They're not interested in that. Where like we say application numerique, you'll be doing it later. Okay. Sebo, have I answered your question?
Yes, you have. Thank you very much.
All right, you're welcome. So here, what is the magnitude of this vector? Because from our equation, this is this cos alpha. So dE. So we just found dE as a vector. It has a unit vector. So this is magnitude and direction. So this is the magnitude part. Therefore, donc dE is equal to sigma ds over 4 pi epsilon 0 r squared. Then, yeah, now we can now put it here in this equation. So dE will be equal to, here we found that it was sigma over 4 pi epsilon 0. What else was there? Okay, over r squared. That's all. Yeah. Then here we're going to have okay, here we have ds. Then there's cos alpha here, cos alpha over r squared. Then use it. Oh, however, this is a method where you're doing your calculations, then you identify that, okay, this is none other than solid angle. At the beginning, remember, whenever you find ds equals alpha something squared, just know that this is solid angle. Toujours. N'oubliez pas, ça c'est solid. So it's ds, so it will be d omega. This was solid angle for people who attended the session for solid angle. Although dE can be instead written as sigma over 4 pi epsilon 0 over d omega. Have you seen how solid angle simplified our equation? Our equation had a lot of variables. Okay. Normally, for direct calculations, you have to find what ds is, find what r is, so that you find r squared, find your cos alpha is. That's what we call direct calculations. But for solid angle, it's just simply grouping up these terms that give us the formula for solid angle. Or, however, ds over r squared, that's how we solve cos alpha, etegara solid angle. Elementary solid angle to be more specific. So we find that our equation has just simplified to this term, and solid angle. Okay, now this dE was just for a smaller charge because it's much easier to start with a smaller portion of the entire thing. But here, our interest is finding for the entire thing. So you just integrate. So whenever you integrate here, you find that passing from here to the total E now, E will be equal to sigma, because this is a constant, 4 pi epsilon 0. Then you just put omega, a solid angle, on which, from elementary to solid angle on which we see the disk. Then from our calculations, we even calculated when I was teaching you about solid angle, we drew some cone in the disk, if you remember. And I told you to find the solid angle on which we see that disk. Always the solid angle, so you have to know the solid angle on which you see the disk is equal to what? 2 pi 1 minus cos alpha, if I'm not mistaken. As simple as that. So you see the solid angle on which you see the disk. So where the solid angle? Because you know the solid angle on which you see the disk, you just put sigma over 2 pi epsilon 0. Then you put 2 pi 1 minus cos alpha. So with this, you only have to know what the solid angle on which you see the disk. You have to know how to decompose a vector when you have a right angle triangle, how to parameterize, you do all this. You just need to do a bit of practice. Then also identifying that, okay, the only component to provide will be x component. Then also finding dE. By finding dE, first you find the dE, you find the general formula for dE. You just give it what you want. You can give this distance between them r or l or whatever. Then this is alpha. Then when you find this, you're going to have this. Then you just compress it. Then you're going to identify it. Okay, these all variables are just other than solid angle. Then for me now to find the entire thing, I'm going to have total solid angle. Oh, the solid angle which we see the disk is what? 2 pi 1 minus cos alpha. You can sort out this one, but I gave you a homework on this one. Okay, as simple as that. You should look at a video, you find that it's simple. And then this 2 pi, there was 2 pi here, no, there was 4 pi. This pi and pi can cancel. 2, 4 will be 2. So here you're going to have sigma over 2 epsilon 0. And you're going to have 1 minus cos alpha. Okay. So this will be the answer for, will also be a valid answer for what? For the disk. So show electrostatic, Creer and disk. If you just give your answer, so your answers will always be variables as well. This will be the answer, simple as that. If you want, you can do some bit of algebra and find cos alpha. It's very, from your diagram, you can find cos alpha. Okay? You just parameterize, you say this is your R or L, and this is R. Then you say cos alpha. Here, let me even put my diagram here. But here, the answer is okay. I'll mark you. So, so you have a right angle triangle like this, if I'm not mistaken. Then this is alpha. Then this is, maybe I'll call this L. Okay. Then this is, I'll call this R. You just call these letters whatever you want to call them. Then cos alpha will be equal to what? What is cos alpha? Cos alpha is equal to opposite. Then I'll call this Z, because this is in the Z direction actually. If you go back there. Cos alpha is equal to what? Cos is equal to adjacent Z over hypotenuse L. Oh, what is L? L is the hypotenuse. So L squared, actually L is equal to the root of R squared plus Z squared. Okay. So here on cos alpha, I'll have Z over the root of R squared plus Z squared. Okay. So if you want, if you understand, you find that because we found for the disk and we found it was 1 minus Z, if you remember, R squared plus Z squared. It was something like this, except that here where there was 1, we put Z over Z, okay, which is the same thing. So if you remember, this was the disk, if you remember this equation. Okay, so Why the question is, why did I decide to go further than not complicating your life and finding what cos alpha is? Because if I tell you that from here we said a disk, last time we said a disk can be visualized to be, or a plan infini, sorry, a plan infini can be visualized to be a disk with radius that approaches infinity. So imagine this r, from the y parameter situation, I said this distance, I called it r, that is the radius. So if this goes to infinity, so if r goes to infinity, what is going to happen? So if you've learned analysis, you find that we have a constant over something that is going to infinity. Constant over infinity is equal to be zero. So on the DWI, whenever you hear the question on the DWI, just know that you're going to get your answer from the previous answer. So on the DWI, the show electricity Creer per ampere infini. When we are from calculating using theorem de Gauss. Okay, but we can also in the DWI, I said we can also in the using the disk. So where there's R, you just put infinity. So E plus infini is equal to sigma over 2 epsilon 0, and it was just this, okay, over 1 minus this. This was z over infinity squared plus z squared. Now this will be 0 because we are dividing by infinity. Okay, so it's going to be sigma over 2 epsilon 0 multiplied by 1 as the answer. Then you just put the direction which you know it's always in the direction of z. So this is for the plan infini. So as you see, it has given us the same answer. Different method, same answer. Though you don't even have to know theorem de Gauss what. So with this method, you can actually do for both. You can actually calculate for the disk. Then once you calculate for the disk, you can now once you calculate for the disk, you can now on the DWI for the plan. If you don't find, if you find the I gave you for finding a disk a longer method, actually a direct method. If you don't understand that one, you can just watch for this one for Solide. Actually, it's more straightforward and simple. There are no a lot of calculations. You just have to know certain parameters and how to parameterize the situation. Even for the plan fini, if you have forgotten how to use the theorem de Gauss, no, theorem de Gauss, you have to know it. I might want you to know how to apply the theorem de Gauss. So that one, it's 90% chance that it might be in an exam, because I want you to have to, before you go to your school, you know how to apply theorem de Gauss. But I can also tell you calculate the show electricity Creer per and Disque. Then I can now tell you on the DWI, the show electricity Creer per the plan fini. Or if you can't manage to find cos alpha in this way, what you just need to do is that the plan fini, will now be a disk with radius that goes to infinity. Okay, let me actually show you a picture so that you understand what we're talking about. Okay, no, not here. Image. So a disk is actually visualized to be a plan fini. Here. Mhm. I hope you're able to see the pictures. You're able to see the pictures, right? Cholo.
Yes, we're able to see them.
So the plan infinity, we take the radius to going to infinity because this continues going. So if you find the disk, you just say from the answer there will be, it will be as a function of radius. So you just say radius to infinity, and something will be zero when you divide something by infinity. Okay. So if you want, you can just say a solid angle on which you see the plan infinity. Solid angle on which you see the plan infinity. It's like uh, the demi-espace. The plan finishes on like half of the surface. So a solid angle on which you see the plan fini. Here, a solid angle on which you see a plan fini. A plan fini is on the we said demi-espace. We looked at solid angle. If you remember, here you can just go directement. If they tell you to find on the do for the plan fini. So a solid angle on which they see a demi-espace, the space where the plan fini is. You just say, oh, this formula is as a function of solid angle. we know that the solid angle in which we see the demi-espace is equals to 2 pi. For the whole space is 4 pi. So here you just put sigma over 4. Let me do this. Sigma over 4 pi epsilon 0. Then you put 2 pi here. Okay. Then you can cancel this 2 pi. Here you're going to have sigma over 2 epsilon 0. It has given me the same answer. So if you are able to remember a solid angle on which we see the plan fin, which is 2 pi, you can just put here, or you can go on, you give me cos alpha, or where is alpha you can, or then where there's alpha you don't plus it. Or here where is alpha you can say pi over 2, whatever works for you. Okay, so that's everything. So now let me summarize what we've done, and make sure you watch this video, and all the best in the exam that I'll give you. If whatever notes that you get, let it not discourage you. It's just me, and it will be a good thing to remind you. Just attempt, even if you're not confident, just try to study. You'll find that okay, so now whenever you have a disc, I think that's 15 minutes. Okay, I'll be a bit fast. You first draw a disc. You first draw a disc, then you draw, oh no, you can start with the z-axis, because you already know if I'm a disc, I'm a plan fini, you already know that it's only have one direction, z direction. Then you put your disc like this. Then you position your point M. You say the point M, maybe the point M is here. Then you just get a smaller portion of the disc. Then you call this dq. Okay. Then you parameterize it. You know that E will be in this direction. So since we are working with a small portion, this will be dE as a vector. I'll even put like an arrow here to show it's a vector. You can now complete this into a right angle triangle. Okay, and you can now call this alpha. Oh, whenever I have a right angle triangle, this dE can be decomposed into two components. One in the z component, that is upwards. So the adjacent side, actually, you don't even care about the other component, actually. Why don't you care? Because you know that from symmetry, we know that dE or E will have only one component, that is will be in the z direction, will be written as dE uz. Okay. So now, you only the z direction. This is the z direction. So you only know you only give me the component of dE in this direction. So what component is adjacent to this angle? You say magnitude cos alpha, as simple as that. Then here, so dE will be written as dE cos alpha uz. So now your job is to find dE, which is the magnitude part. What is dE? dE, how do you define dE in general? Let's say the distance between this point P and M is R. Okay, so we define the magnitude part where without even involving the unit vector, we define it to be what? We define dE to be the charge dq over the constant. Then usually it's PM vector over, if you don't want to be confused, the magnitude of the power 3. So if you say the magnitude of PM is R, then the unit vector is UR, which means PM is a vector. It has both magnitude and direction. So you're going to have dq over 4 pi epsilon 0. Then where is PM, you put magnitude and the direction, which is unit vector, represent direction. What is PM? Magnitude of PM to the power 3 is just R to the power 3. Then this can cancel this R,
Yes.
can cancel. We're going to have dq over 4 pi epsilon 0, then R squared. You even ignore the unit vector because here there's no R here, so you're just getting the magnitude part of the vector. So if this was dE, so for you to get dE, you ignore the unit vector. So you're going to have this. Then you can now remplace whatever you have. You can now remplace. Oh, before you remplace, you also always remplace dq by its surface density expression, ds, as simple as that. Now you can remplace in the equation. Okay, so dE, which is given by dE cos alpha in the direction of uz. So where dE was given by sigma ds over 4 pi epsilon 0, then you're going to have ds, or you already have ds, sorry, cos alpha over r squared, then in the direction of uz, of course, in the direction of z, of course. Now, this term here, this term is just now you identifying what is this term here. This term is none other than, whenever you have, I said whenever you have surface cos alpha over something squared, this is none other than me, elementary solid angle. So dE can be written as the elementary solid angle sigma over 4 pi epsilon 0. Then that's the beauty of solid angle. You find that you eliminate a lot of terms just by putting the omega. Then you just have to know the solid angle on which to see the plan finish is what. Then for you now to find the entire surface, what do you do? For you to find for the entire surface, you say E, therefore E will be equal to sigma over 4 pi epsilon 0 omega instead of the omega. D, you forget about the d what now. Okay. Then you just say, okay, the solid angle on which I see the disk, or you calculate this solid angle on which you see the disk. What is the solid angle on which I see this? Sigma over 4 pi epsilon 0. The solid angle on which you see the disk is 2 pi 1 minus cos alpha or cos theta, whatever you want to put. Then now, this is the answer for me. Or if you want, you can come back to here and say, okay, the length here, okay, this length I'll call it L, this one is R. Then you can find cos alpha and L. Then we're going to plus a, but what you can just do is, this is the answer for the solid angle on which you find oh, this is for the disk. Okay, the short episodes I take for the disk. Then you can say, or the solid angle on which what's going on with what's going on here. What's going on here? Okay. So now you can say, oh, then they can say now on the dui, that is deduced from the answer you found. We know that a disk is just a plan infini if the radius goes to infinity. Okay. Or since here we're dealing with solid angle, you retain this formula which is solid angle. We know that E for the disk is equal to sigma over 4 pi epsilon 0 solid angle. Then solid angle on which we see, because the plan finis on like the Demius pass, and the solid angle on which we see the Demius pass is 2 pi. We learned about this. So sigma over 4 pi epsilon 0, then 2 pi. Then this is going to be sigma over 2 epsilon 0, which is always the same answer. This is always for the plan. Then you just put the direction, this is the direction, because this is a vector. As simple as that.